Okay, now I'm recording it. And so we covered these parts in the practice worksheet for the final exam. So we looked at the vapor pressures of different objects. And here you need to look at the vapor pressure given in torr. And if the question is giving you in torr, but you need to find it in ATM, so make sure you do the conversion on the side on the paper, and then you find the dots on the graph. So this thing, something you have already done. Next, you need to find out, these pressure, temperature, PT diagrams, and here you should know the specifics of it. So just pay attention. If the question is asking normal boiling point, that means that normal boiling point, 1 ATM. And if you are given the graph in ATM, then do that in ATM only. But if the graph is given in torr or in millimeters of mercury, either you do the conversion or you extrapolate based on the numbers given. So in this case, for the torr, 760, that's the number you're going to look on the graph for the normal boiling point where the liquid is converting to gas, and for the melting point where the liquid is converting to solid. Now, next thing is this problem number 13, where we're looking at the polarity of the molecules and the molar masses and finding the boiling point. So the general rule is that higher the boiling point, the higher the molecular weight, the higher the boiling point is. But then we also look at the intermolecular forces. So the more the intermolecular forces, the more the boiling point is. So in this case, we are given the values of the dipole moment. So the higher the dipole moment, the higher the boiling point is. So that is why acetonitrile is high. Then you need to know the heating and the cooling curve. So you need to know that these are the, these are the heat of vaporization, and this is the heat of fusion, where the liquid and the gas coexist, and in the heat of fusion, the gas and the solid and the liquid coexist. So this is the heat that is required to fully convert from one phase to another. But on the other hand, the heat capacity of the substance is the amount of heat that it can absorb before any change of state takes place. So these are the heat capacity values, where you see solid going to liquid, liquid going to solid going to, or liquid continues to absorb until it boils. So we also can be asked a question, where is the melting point? So this is the melting point of a substance, and melting point and freezing point coexist. So keep that in mind, that this is where the liquid and the solid are found together. So this is something you can determine from the heating and the cooling curve. Next, we looked at the heat of vaporization values, and we looked at the different substances. Now here, the heat of vaporization, as we discussed, is the heat required to convert the liquid to a gas. So the maximum is for water, and for the ethanol also, it's close, because both of them have largest number of intermolecular forces. So they are very strong network, very difficult to break. That's why they need more heat to dismantle that. Next is the important question that can be asked is the calculated URMS3. Now here we write down the formula, 3RT over M. M stands for the molar mass. Just make sure that you convert the molar mass from grams to kilograms. So that's one piece. Next is convert the temperature from Celsius to Kelvin. Now the last piece is convert the joules to kilograms, meter square and second square. So just write, instead of joules, write down kilograms, meter square over second square. So the rest is you solve and you get your answer. Next, we are looking at the water displacement method. Here, the question is asking you find the partial pressure of hydrogen. So we use the Dalton's law and we get 753.26 torr. But pay attention, the question is asking you for the ATM. Okay, so we know that 760 torr is equal to 1 ATM. So 753.26 torr into 1 ATM over 760 torr. What do you get?
0.991.
Yeah, so that's the answer. Okay, so this type of question can be asked.
I have a question about that one.
Yeah.
Wouldn't the total pressure be the 766, not 760? Because it said a barometric pressure of 766 torr.
Oh, okay. Yeah, that's right. Yeah, 766. Yeah, 766. Typo error. So yeah, so then it changed. Now then what does it become? 766 minus 26.74. 766 minus 26.74. 739.26.
Professor?
Yeah.
Is it more supposed to be like around 739.26?
739.26. Yes, you're right. Thank you, Tristan. Yeah. 739.26 store. Yeah, because there was a typo error made from my side. This was sorry about that. This was 766 and not 760. I made a mistake in putting down this number. Okay. So just fix it. All right. Let's look at the next one. Is in this case, yeah. So this is actually similar to this one, like just a part of it. So broken down. So here in this experiment, 210 milliliters of wet hydrogen is collected over water and the barometric pressure is 765 torr. How many grams of zinc have been consumed? So first thing you're going to do is find the partial pressure of hydrogen. Okay. From the formula, P total is equal to P of hydrogen and P of water. So something we did just now. So let's do this. 765 torr is equal to partial pressure of hydrogen plus the partial pressure of water, which is given to you in this case is 26.74. 26.74 torr. So 765 torr minus 26.74 torr. What do you get? 765 minus 26.74. 738.26. 738.26 torr. Okay, but the problems we are going to be using the ideal gas law. So we need to convert the torr to ATM. So convert torr to ATM because we're going to be finding the moles of hydrogen. So 1 ATM is equal to 760 torr. So 738.26 torr times 1 ATM over what is that? 760 torr. So what do you get? 738.26. Divide that by 760, and here you get 0.971 ATM. Always write the units and the context in which you are doing these calculations. So we are finding the now moles of hydrogen. Why do we need to find moles of hydrogen? Why? Why do we need to find moles of hydrogen? Yes. Explain.
Because we need to find the moles of hydrogen to then find the moles of zinc.
Moles of zinc, very good. So because the question is asking us to find the grams of zinc, okay, grams of zinc. And here we are given all the information about hydrogen. So if we know how many moles of hydrogen we have, we can find the moles of zinc, conversion factor, and then from the moles of zinc, we convert it to grams of zinc. Okay, so let's do this. How do we find the moles of hydrogen now? From what we know the partial pressure of hydrogen, we know the volume of hydrogen. Okay, we have eliminated the partial pressure due to water, so we know the volume of hydrogen. Okay, we know the temperature at which this is done. We got the partial pressure. So PV is equal to nRT. Okay, that's the ideal gas law. So N for the hydrogen is equal to PV over RT. Okay. Now partial pressure of hydrogen was 0.971 atm. Okay, atm, right? Times the volume. Now convert the volume into liters. So always do this conversions. Convert milliliters to liters, degrees Celsius to Kelvin. So 206 milliliters times 1 liter over 1000 milliliter gives you 0.206 liters, and 27 degrees Celsius plus 273 is equal to 300 K. Okay, so now we know the value of R, we already know 0.08206 liters times atmosphere. Is it? Oh no, sorry, it's the other way around. Multiply that by volume. The volume is 0.206 liters over R is 0.08206 liter atmosphere per mole K times the temperature is 300 K. So calculate this. So 0.971 times 0.206 is equal to 0.200, and that's 0.08206 times 300 is equal to 24.61. So 0.200 divided by 24.61 is equal to, so the number of moles of hydrogen is coming out to be 0.0081 moles, because the mole to mole ratio, moles of hydrogen and moles of zinc are the same. It's 1-to-1 ratio. Therefore, the moles of zinc is equal to 0.0081 moles. Right? The conversion factor, right? From the balanced equation. So it's important to always check the equation. Got it? Next is convert. The fifth step is convert the grams. Convert to grams. You take the moles. What is the molar mass of zinc? 65. So 0.00, so moles of zinc to grams. So 0.0081 moles of zinc times 65 grams per 1 mole. And so that's basically 0.0081 times 65, and you get 0.52. 0.528 grams. Okay, so the closest answer, because we round up and all that sum, that's the closest answer. So just choose the closest. Okay, so it's B is 0.519. Okay, got it? Okay, so again, these are important questions. I'm going to just mark them red. So please just make sure that you guys practice these. Put them in order or steps or whatever works for you. Okay. Next is on the mole fraction. Mole fraction. So mole fraction, the formula for the mole fraction for any substance. So we are finding the mole fraction of krypton. Krypton is equal to partial pressure of krypton over the total pressure. Now, last time some of you had actually also calculated the number of moles, or that you went into too detail. Some of you, I noticed that. But use this formula and use this formula. P total is equal to P xenon plus P krypton plus P argon. Okay, let's do this one quickly. Okay, so total is 6.69 ATM. I'm going to write it over there. Okay, now P total is 6.69 ATM is equal to partial pressure of xenon is 1.92 ATM plus krypton, argon is, this one we need to find, and argon is 2.75 ATM. So what is for argon for partial pressure of krypton? You guys do the calculations. What is that again?
2.02.
2.02 ATM. Okay, so next is the the mole fraction of krypton is equal to partial pressure is 2.02 ATM over the total, which is 6.69 ATM. Okay, what do you get here? Okay, so the partial, so this is equal to 0.3012 or whatever. This is the mole fraction. Okay. All right. So same thing. You are given the next one. So the next one is a simple PV is equal to N R T. So P is equal to N R T over V. We need to find the partial pressure of methane gas. We are given the number of moles, which is 0.1135 moles, okay, times 0.08206 liters times atmosphere per mole K, okay, times the temperature is 20.8 plus 273 and 83789 and 293.8 K over the volume, and just make sure that it is in liters. So 171.6 milliliters times 1 liter over 1000 milliliter makes it 0.1716 liters. Okay, liters. Okay, 0.1716 liters. Okay, so do this, and that should give you the partial pressure of methane gas, sorry. So the answer to that is 16 ATM. All right. All right. So next is, what is the density of carbon dioxide gas in grams per liter at the millimeters of mercury and 56.3 degrees Celsius? So you know the formula. The formula density is equal to M. M is the molar mass times the pressure times R over R in T, RT. Okay. So when we talk about carbon dioxide, so first in this case, you will be calculating the molar mass of carbon dioxide. Okay. So get the molar mass of carbon dioxide. Get the molar mass of carbon dioxide. 1 carbon times 12, 2 oxygens times 16. So 12 plus 32 is 44 grams per mole. Okay, so here we are given the molar mass times the pressure. Now in this case, they are given you in millimeters of mercury. So the value of R, you know, either you change it to millimeters of mercury, or you can put the value of R as, which one was that? 62.4 millimeters of mercury times liter over moles K. Or you convert this 1106.2 millimeters of mercury times 1 ATM over 760 millimeters of mercury. Okay, so 1106 divide by 760 and you get 1.45 atm, and you use this number. Okay, and temperature 56.3 degrees Celsius plus 273. So 56.3 plus 273, and that is 329.3 K. Okay, so the rest is just density is equal to 44 grams per mole times pressure is 1.45 atm over 0.08206 liters atmosphere per mole K times the temperature. Sorry about that. Okay. Temperature is, which one was that? 329.3. 329.3 K. So what do you get here? So 44 times 1.45 is equal to 63. 63.8. 63.8. Divide that by 0.08206 times 329. 329.3, and you get 27.0. So 63, sorry. So here 63.8 divide by 27, 2.36. So that is equal to 2.36. And your answer, the closest answer is, so this is grams per liter. So if you look at here, the moles and moles cancel out, ATM cancel out, K and K cancel out. So you're only left with grams per liter, and that's your closest answer. Okay, guys? All right, let's look at the next one. So I'm just going to write down the steps here. So first is how many grams of calcium hydride? So we need to find the grams of calcium hydride are needed to generate 48 liters of hydrogen gas. So we are looking at the hydrogen gas at a pressure of 0.99 atm and a temperature. So you look at it, the volume is given, the pressure is given, and the temperature is given. What can you find when you are given the volume, pressure, and temperature of one gas? And in this case, or something. So we are given the pressure, volume, and temperature of hydrogen gas. And we can find, so find the moles of hydrogen gas. How? PV is equal to nRT, N is equal to PV over RT. So this N of hydrogen, this is equal to the moles of hydrogen gas, okay? Next is you are going to take the moles of hydrogen gas and you're going to convert it to the moles of calcium hydride, because that is our final, what we are interested in. So that's a roadmap you're following, okay? Once, how? Using the balanced equation, mole to mole conversion, okay, mole to mole conversion. So we see that 2 moles of hydrogen are giving or are produced when 1 mole of calcium hydride reacts, okay. So the moles of calcium hydride, you're going to do this. You're going to put this, solve this, put this problem like this. Moles of hydrogen times the mole to mole ratio, which is 2 to 1. So 2 moles of hydrogen and 1 mole of calcium hydride. So this is how you will set up. So this is going to give you the moles of calcium hydride. And the next is convert that to grams of calcium hydride. So you take the moles of calcium hydride and convert that to grams using the molar mass. So this is the molar mass. Molar mass over 1 mole of calcium hydride. So basically multiplying those, okay? And that's going to be, that's your answer. Okay, so your answer should come out to be this. So this was on test. This was a test question. I made some corrections over there for you. That's going to give you in grams. So here you would need the molar mass of calcium hydride. Okay, so these are the steps. Okay, next, how many moles of gas are there in the liter? So this is just the, you know, the PV is equal to nRT, that formula, N is equal to PV over RT. Just use that. Okay, next is the molecular geometry of borate ion. Okay, now here, this question, these type of question ask you to look at the Lewis structures. So let's do this question because it's an important question. So something similar is going to be on the test. Okay, similar, not exactly this, but similar. Okay, what is that? All right, here you are, how do you calculate, how do you do the Lewis structures? What do you do first?
Total valence electrons.
Total valence electrons, very good. So for bromine, and in this case, there are 3 oxygen. So 1 bromine and 3 oxygen. Bromine is bringing 7 valence electrons, right? And oxygen is bringing 6 valence electrons. So we have 7 coming from here and 18 coming from oxygen, plus there is 1 more electron. So that's going to be 1 more. So total is how much? How much? 26. So we are looking at total, to place total valence electrons, 26. Okay. Now 26 valence electrons. Next, what will you do next?
Central atom.
Central atom, very good. How? Good. So we see that the electronegativity of bromine is less than the electronegativity of oxygen. So therefore bromine will be in the central atom. That's one thing. Second thing is that bromine can make 1, 3, 5, and 7 bonds, and oxygen can make only 2 bonds. Okay, so bromine will go, and anytime bromine connects with oxygen or chlorine or iodine, these guys, they can make 3, 5, and 7 bonds. Okay, so now you are going to place bromine in the middle. Bromine is in the middle, 1 oxygen here, another here, and then the third one here. Now, what are you going to do? Connect them with the single bond. So 1 single bond, another one, and another one. How many electrons did we use? 6. So we are left with 6 electrons are gone for the single bonds, and we are left with only 20 electrons. So you fill those 20 electrons, fill the octet of the outer atoms with the 20 electrons, or octet of all atoms, starting with the outer one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And the remaining 2 will go where?
Central atom.
Very good. Goes on the central atom. So now you are going to rearrange, because even though you see that oxygen's octet is met, but the need to make 2 bonds is not met in case of oxygens. Okay, so that's why you rearrange. So in the rearrangement, remember that bromine can make 1, 3. The bromine is fine. It's making 3 bonds, and bromine can defy the octet also. So bromine's octet is met, oxygen's octets are met, but they're not satisfied because the need to make the bonds, 2 bonds for oxygen is not mixed. So therefore, but remember, bromine can only accommodate up to 7, 5 and 7. So here, when you do that, in that case, bromine will make 4 bonds, which is not feasible. You do this, bromine makes 5 bonds, which is feasible, but bromine cannot make 6 bonds. Bromine can make 7 bonds. So only this arrangement will be possible. So here we see that the bromine is in the middle, and you have 1 oxygen here, which did not participate in the rearrangement. These 2 guys participated in the rearrangement. Okay, so 1, 2, 3, 4. 1, 2, 3, 4. Now, where is the negative charge? Where is the negative charge? The 2 oxygens are making double bond. Octets are met. Very happy. But where is the negative charge? Where will you put the negative charge, guys? On this bromine, on this oxygen, which is looking to have a double bond. Okay, so there is going to be resonance in this molecule because the double bond is going to rotate. So resonance will happen. I don't have much space here, but you understand that resonance would be that the bromine will have, now this guy makes double bond, this one holds the negative charge, and at least its octet is met, and this one is holding, and so this the charge is going to just rotate. And then at one point, this bromine, this one will keep a negative charge, and these 2 guys are making the double bond. But the question is not about resonance. The question is about the shape. Okay, about the shape. So how would you determine the shape now?
Number of electron groups.
Yeah, so you can refer to the table. Okay, you can refer to the table. Where is that table? Did it come out to be bipyramidal or pyramidal? AX3 is pyramidal. Okay, AX3. Okay, so this is trigonal pyramidal, and this shape, the way you are going to do is first finish this Lewis-Strauss structure, account for all the 26 electrons, and then you look at it, the central atom with respect to the central atom. So bromine is the central atom. It is bonded to 3 oxygens, so that is X3, and it has got 1 lone pair. So there are 4 electron groups, and these 4 electron groups are relate to AX3E1, which is molecular geometry is. Molecular geometry is from outside, and that is the trigonal pyramid. Okay. Now we're going to look next is that is the xenon in XeF4 molecule has. Now in this case, you have to draw the Lewis structure. So sometimes the question is not going to state directly, but that implies. Okay. So xenon with F4, 4 fluorines. So there are 8 electrons in xenon and 4 times 7 electrons. So 7 4s are 28. 28 electrons are coming from 28 electrons are coming from fluorines. 28 plus 8. How much is that? 28 plus 8? 36 electrons total. Okay, that's always total valence electrons. All right. Now, which one is going to be in the middle? Xenon or fluorine? Xenon, because the electronegativity of fluorine is higher than xenon. So xenon will get the central spot. Besides that, xenon, fine, doesn't make bonds, but in special circumstances, it can make 2, 4, and 6 bonds. Okay, so put xenon in the middle, and you put fluorines on 4 sides because there are 4 fluorines, and you connect them with single bond, and we have used 1, 2, 3, 4, 5, 6, 7, 8. So we have used 8 electrons. We are now left with 28. So 36 minus 8 is equal to 28 electrons left, which are used to fill the octet of the outer atoms. Okay, 1, 2. So here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 electrons have been used up, right? And we are left with 4 more. So they are going to be on the central atom. So 1, 2, 3, 4. So xenon now, just rearranging also sometimes is just cleaning up, because the lone pairs, Vasper theory is stating that these lone pairs do not like the bonded atoms, so they push them on, either side and as far away from each other, because there is going to be repulsion between the electrons. So all the fluorines, the bunched up in one side, or just like we looked at the shapes earlier, flat bread, oh, 1 second, which is pierced from the center. So sorry about that. So here is this fluorine. So like a bread which is pierced from the middle, like that type of a shape. Okay. So in this case, how many non-bonded electrons are there? Non-bonded electrons and bonded electron pair. 2 non-bonded electrons. They are 2 non-bonded, 2 pairs, in other words, electron pairs, right? So this is 1 pair, this is the second pair. So that's 2, and there are 4 bonded electron pairs. So these are pairs, but they are bonded electron pairs. So these are, sorry, that one is, these are just the electron pairs. Okay, so the answer is D. Okay, all right. Next is the molecular geometry of the leftmost is which one? What is the molecular geometry of the leftmost, which is CH3? It's just, carbon with 3 sides, that's tetrahedral. You should be able to recognize that by now. Okay, next is rightmost carbon is bonded on 3 sides, right? So it is like a planar, trigonal planar. Okay, let's do this one. PCl5, how many electron domains does it have? So PCl5, phosphorus, same thing here. In this question, they are asking you to draw the Lewis structures. Okay, though you may think that you don't need it, but draw the Lewis structures. Lewis. Okay, so here you have, okay, P, phosphorus is bringing 5 electrons and chlorine is bringing 7 electrons. There's only 1 phosphorus, there are 5 fluorines. So we are getting 7 5s are 35 plus 5 is 40 electrons in the system. Phosphorus makes 3 and 5 bonds, and chlorine makes, yes, 1, but chlorine can make 3, 5, and 7 bonds. But pay attention here. This only happens if chlorine bonds with more electronegative atom, such as oxygen. Okay, but the electronegativity of phosphorus is less than the electronegativity of chlorine. Chlorine is bonding with a less electronegative atom. So therefore, chlorine is only going to make 1 bond. So phosphorus will be in the middle, chlorine's on the side, and so 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 8 have been used up, and we're left with 32 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 32. So this goes in the middle. So PCl5 has how many electron domains now? How many electron domains?
2 lone pairs.
Well, wait a minute. In this, okay, so there was a little error I made here. So it is 40 electrons, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 got used up. And we are only left with 30 electrons. And the remaining 30 go on the chlorine. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. All of them got used up. So that is why there are 5 electron domains or electron groups, right? And what is the molecular arrangement? So it's back to your table from the Lewis structure table. And in that table, this is going to be AX5, okay? So 5, so that relates to, on the table, look at the molecular geometry and the electron group geometry. Look at the molecular and the electron group geometry. So which one is it? AX5 is trigonal bipyramidal, is the molecular. And the trigonal bipyramidal is the, so molecular is, so wait a minute, trigonal bipyramidal. So molecular, pay attention to this number, this word right here. If they say electronic, if the question was asking for electronic geometry, then you would have looked at that other table and it would have been, in that case, trigonal bipyramidal. So both of them are the same, you know, but sometimes the names are different. Like, for example, the seesaw in one is the trigonal bipyramidal in the other one. Trigonal bipyramid, like two things of pyramid. Okay. Okay, so let's look at the next one now. Okay, now let's look at the hybridization. The hybridization of carbon atom labeled X in the molecule below. So we are looking at the hybridization of this carbon atom. So for that, you are going to look at how many electron groups are around the carbon atom. So on carbon atom. So how many electron groups are there? How many electron groups? 3. Everybody agree to that? Mm-hmm. So the 3 electron groups correspond to what type of hybridization? S, P, the total has to come out to 3. So what is that? 2. Very good. So sp2, B. Got it? And in case you don't, then you can always look at the handout also. So these were given to you in the class and they're also on the module. So look at the handout in case you are confused. Okay, next is the hybridization of oxygen in this molecule. So oxygen, same thing. Oxygen, the one marked X. How many electron groups on X? Yes. Oxygen has 2 lone pairs, right? And it has got 1 double bond. So it comes out to be 3 electron groups. And these 3 electron groups always relate to sp2, B. Okay? Now the carbon hydrogen sigma bond in ethylene results from the overlap of what? So here, yes, this is the sigma bond and the top one is the pi bond, right? So let's write this down a little bit differently here. So this is here, CH2 looks like this, double bond, carbon, and CH2 is here. So now look at the electron. So first remember that pi bonds are made by the pure P. Okay, and they are made by the sideways overlap. Sideways overlap. Okay. All right. So in this case, the question is the carbon hydrogen sigma bond in ethylene results from the overlap. So hydrogen is obviously bringing the s orbital. It's the 1s1. Okay, the s is coming from the s is 1s1 is of the hydrogen, and but carbon what is the hybridization in carbon? How many electron groups on carbon? That's what you need to see. 3 electron groups relate to sp2. So this sp2 orbitals are the ones that are making the sigma bonds. Okay, so sigma bonds with the 2 hydrogens and with the other carbon. So 2 with carbon makes 3 sigma bonds, but let's look at this. Carbon making 3 sigma bonds. Okay, and this carbon, starred carbon. 2 sigma bonds with hydrogens and 1 sigma bond with the other carbon. Okay, so the answer sp2 hybrid is for the carbon and sp3 of the hydrogen. The pi bond results from the overlap of what? Now let's look at the pi bond in this case. So same thing, carbon sp2, this is the sp2, 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 this is the other carbon sp2, and then this hydrogen and this hydrogen. So here they are overlapping with the hydrogens, forming a sigma bond, and this is the sigma bond with them, the single bond. That's the hydrogen, hydrogen, and hydrogen, and hydrogen, okay? And that's a sigma bond here and sigma bond here, sigma here and sigma here. Now we are talking about the pi bonds. So in this case, carbon makes 4 bonds, so one of this is not going to be like this. This is a pure P and this is a pure P. Okay, now here is 1 electron and this is another electron. So in this case, these are the p atomic orbitals which do not mix. They are the ones that make the pi bond. Okay, so that's the hybridized structure also. Next is, what is a typical double bond? What does it consist of? 1 sigma. Double bond consists of 1 sigma and 1 pi. Double bond always 1 sigma and 1 pi, and triple bond consists of what? 1 sigma and how many pi's? Yes, 2 pi's. Okay, so 2 pi's. All right, next is the NH bond in ammonia consists of how many sigmas and how many pi's? So here you need to again draw the Lewis structure. So here's the ammonia double bond, lone pairs. So now how many sigma and how many pi?
3 sigma.
3 sigma and 0 pi bond. But remember, the question is asking 1 NH bond. NH bond, not the entire ammonia molecule. So yeah, we looked at the entire ammonia molecule, but here's the NH bond. So 1 NH bond consists of only a sigma bond. So this is 1 sigma. This is 1 sigma. Oh, 1 sigma, 1 sigma, 1 sigma. Okay, so 1 NH bond is just 1 sigma. Okay, next is, I think this one was on the exam or something, the hybridization of iodine in IF3 and IF5 or what? So let's do this one. That will give you a practice on hybridization also. So IF3 hybridization in this case. So always in this case, never, even if they don't ask you, still draw the Lewis structures. So iodine bringing 7 electrons and fluorine bringing 7 electrons, but there are 3 fluorines. Okay, so 1 iodine bringing 7 electrons. So here we see 7 and 7 threes are 21. So 28 electrons in this case, and iodine with fluorine 7 times 1 and 7 times 5. So we see here 7 electrons coming from iodine and 7 5 are 35 electrons coming from here. Then this becomes what? 32, 42 electrons. So put iodine in the middle, fluorines. So there are 3 of them. So, in the beginning, you should just put them like, like that. And then 5, 1, 2, 3, 4, and 5. Connect them, 1, 2, 3. 1, 2, 3, 4, 5. So we used 6 electrons. 28 minus 6, 22. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 20. Okay. The next one is 42. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 use 32 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. So in this case, you see, there are 2 lone pairs. 2 lone pairs. And in this case, there's only 1 lone pair. Okay, so anyways, the electron groups. So we see 1, 2, 3, 4, 5 electron groups. And in this case, 1, 2, 3, 4, 5, 6. There are 6 electron groups. Okay, so 5 electron groups relate to S, P, 3, D. So 4 plus 1, 5. And this one relate to S, P, 3, D, 2. So here you can refer to the handout in case in case you don't remember or something. So just count the electron groups. Count the electron groups. All right, guys. Okay, the next one, you guys will do it. Bromine, same story, same way. Okay. The hybrid orbitals used for bonding by the sulfur atoms, same thing. The hybridization of terminals, same, we covered all this quite a bit now. Based on the molecular theory, molecular energy diagrams. Now, okay, let's do this one, MO diagrams. And so here, let me put this in red. Okay, this one is just the hydrogens, like just the s orbital. Let's look at this one. Which of the following molecules would you expect to be attracted in the magnetic field? Draw the molecule of fluorine, nitrogen, and oxygen. So remember the templates. Some of you made mistakes on the templates. Which template to use? So let's get the templates first. Here are the templates for the nitrogen, oxygen, and the fluorine also follows the same thing. So now we are looking at draw the molecules, your molecular orbital diagrams actually for fluorine, nitrogen, and oxygen. So let's do for the nitrogen first. Nitrogen. So we are looking to place how many electrons for nitrogen? Just look at the valence electrons. Okay, only look at valence electrons. So nitrogen, how many valence electrons? One nitrogen is bringing how many valence electrons? How many? 5. And the other nitrogen is also bringing 5. So we are going to place a total of 10 electrons for the nitrogen. So 1, 2, 3, 4. Now pay attention. First singly occupy and then you pair. So the Holmes rule still follows. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, Okay. 9, 9, and 10. So we used all the electrons in this set. Then comes oxygen. Oxygen, each of the oxygen is bringing 6 electrons. So we are looking to place 12 electrons. So here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So there are 2 unpaired in this case. Okay. Now let's look at fluorine. Fluorine is bringing 7. So that's 14 electrons. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay. Got it? So the mistake some people had made was they kind of knew how to do it, but they made the wrong templates. They used the wrong templates. So just make sure that if you use the right templates, then everything falls in place. Okay, then next is, which one would be attracted to the magnetic field? Which ones get attracted to the magnetic field? Yes? The ones that have unpaired electrons. The ones that have unpaired electrons. Unpaired electrons. In other word is paramagnetic. So now tell me which ones? Which one? Oxygen. So oxygen is the only one that is paramagnetic. So this one would be attracted to the magnetic field. Nitrogen and fluorine will not, because all the electrons are there. Okay?
Can we go over 74 since we're short on time? That's from chapter 5.
Okay, yeah, just let me just quickly get through. Yeah, I'll do it. Let's just walk through. Okay, so this one is the using the table bond dissociation. So just remember that here, the reactants minus the products. So that's another mistake students were making. Okay, so you look at and then multiply that. So I think this should be okay. You guys did fine on the worksheet. So look at the bond energy worksheet. So same story, bond energy, you were fine. Now resonating structure, it is the same as the bromate we covered, okay? In bromate, we just like I showed you, the movement of the double bond. So when we talk about the resonating structures, we are actually looking at the movement of double bond. Double bond moves, and with that, you know, with the charge also moves. So charges also move. And for this, I have done this in the notes also. Formal charge. So you should write the formula and show on each of them. On nitrogen, oxygen, you can label it 1, 2, and 3. Okay, oxygen 1, oxygen 2, oxygen 3, and like that. Okay. The phosphate ions, so this is given the this is all, this one you guys can do, these are simple. Which of the following isoelectronic, what do you mean by isoelectronic? What is isoelectronic, guys? Isoelectronic means same number of electrons. So that's what you have to count, okay? So all this is ionization energy and all that. Now here, another thing, third ionization. This is a mistake some students made. So remember that gallium, and I'll just do, this was a mistake I saw. So gallium minus 1 electron makes gallium plus 1. This is the first ionization energy. Okay. Then gallium plus 1 electron plus 1 charge minus 1 electron gives you gallium with plus 2 charge. This is the second ionization energy. That is the energy needed to remove the second electron. Then gallium plus 2 and minus 1 more electron gives you gallium plus 3. That is the third ionization energy, which is to remove the third electron. Okay, so that is why it is this D. Okay. Okay. In which orbital does electron experience the greatest shielding? Shielding effect. So you have to look at the electronic structure of, the electronic configuration, and the electrons that are, the outermost electrons will experience the shielding most and figure out where they are. Okay. Effective nuclear charge is the same thing. Effective nuclear charge means nuclear pull. The ones that are, they get attracted to the nucleus. Okay. The ion with the smallest diameter. So remember that the cations versus anions, first of all. So the cations will be smaller than neutral atoms, and the anions will be cations are smaller than the neutral atoms. Okay, and then the anions are larger than neutral atoms. So that's one piece. Now we are looking at all of them the same. So the ions with the smallest diameter, obviously the smallest one out of this is the lithium, is the smallest. So this is, all this you can do. Quantum numbers, I'll just give you one question from that. No, I may not even give a question. Okay, the electronic configurations, you guys should know. This is the formulas, we covered that. You guys did fine on the test on these. Electronic configurations, just go back and check these. Okay. Now we are looking at the value of delta H, the enthalpy change. Okay, how would you do this one? How would you do this one? Okay, let's just do this one. Here, guys, you are given for this reaction, the delta H value for this reaction is negative 790 kilojoules. All right. Is it recording? Okay. So it is 79. So this is for this one is given. Okay. So 4.9 so kilojoules so keep this in mind that this is for this is sulfur. Okay. So 2 moles of sulfur. Another way of writing this whole thing is also this way. So because it's negative, that means this is, what kind of reaction is this? Exothermic or endothermic? Exo. Exo is always negative delta H value. That means that this is also a part of the product. So this is another way of writing this, 790 kilojoules. Okay. So the relationship now is 2 moles of sulfur is giving off 790 kilojoules of heat. And the other conversion factor is 790 kilojoules of heat over 2 moles of sulfur. Okay, 2 moles of sulfur. Now, the value of delta H for this reaction is this, the enthalpy change. Now, you need to find the moles. So we're not going to do this more, but you just do this. Convert 0.95 grams of sulfur to moles of sulfur. Okay. Next is you take the moles of sulfur from part 1, from the step 1, and multiply that by this guy, 790 kilojoules over 2 moles of sulfur, and you will get the answer. Okay. Next, the value of delta H for the reaction below is this. How many kilojoules are consumed when 5.10 grams of, same story. Here it's the same story. In this case, you have 128 kilojoules as a reactant. This is when delta H value is positive, that means it's endo. Okay, so same thing. Find the moles of carbon monoxide, right? And then you do the same way as we have set it up. So this is the formula. What is that formula? The specific heat capacity of lead is given. How much heat is required? What is the formula?
Q equal to MSHT.
Very good. Q is equal to M times the specific heat times the delta T. So the change in temperature is delta T, which is T final minus T initial. So the T final is 37 and T initial is 22. So that gives you value of delta T. Mass is given to you 15 grams and you're given the specific heat capacity. You multiply and you will get it. Okay. Next is, this is the Hess law. For the delta H for this reaction, this is your target reaction. Okay, target reaction. This is the target reaction. And you are given the steps. So what will you look at in the target reaction? You're going to see that IF5 is on the reactant side. And in this case, the IF5 is on the product side. So what are you going to do? Flip, right? This guy has the IF5 on the product side, but we need it on the reactant side. So we need to flip this one. So when you flip it, this becomes positive 745. Don't forget that. And this, so when you flip it, so flip this reaction. Okay, next thing is you need IF3 on the product side. So which is, in this case, it is good. So we are not going to change it. We will keep it as is. And that will take care of the fluorine. So do you guys want to do these steps or you're okay with that? Huh? Okay, everyone? Okay.
All right, you can do it.
What about the rest of you guys? Huh? Do it? Okay. Okay. So first step, look at the target reaction. Second step, look at the steps. You know, these are the pathway reactions. So look at the pathway reactions, and in the pathway reactions, identify or match. So look in pathways the position of the reactants and the product, and based on that you flip or keep as is. So like I have done. Okay, so now let's do this here. IF is a gas. The states are very important. Plus F2 as a gas, and this gives you IF3 as a gas, and the value of delta H is negative 390K. That is the value of delta H. Okay. Next is we flip that other guy. So, and now this is IF5. Okay. IF5 is now reversed back. So this is giving you IF and gas and F2 as a gas. And now this becomes positive 745K. Okay. And now what will you do here? You're going to see the ones that are on the opposite side. The ones that are on the opposite side are going to cancel out. So you see IF and IF cancel out. Okay, and even in the fluorines, there are two fluorines. So one of the fluorines cancels out. The rest, you just write down here IF5 and nothing else is giving you IF3 plus F2. And now you guys do 745 minus 390. What do you get? Say that again. 355. And this is going to be a positive number or negative number? Positive, because the big number is a positive sign. So positive 355 kilojoules. And that is the answer. All right, so I'll give you like these types, simple ones. But yeah, there is Hess law is definitely going to be on the test. Okay. All right, what about this one? Let's look at this one. Given the following, the enthalpy for this reaction. So here, now I'm not going to do all of it, but I'll just show you again, same thing. So this is our target reaction, and these are the pathways reactions, the top ones. So we need F2O3 on the reactant side. So this one looks good. We need the carbon monoxide on the reactant side, so this one is also good. And the other two are, remember, it's a pathway, so it doesn't matter. So we will keep as is. Nothing changes in this one. Next is iron plus carbon dioxide, gives you 2 carbon monoxide and Fe2O3. And here, Fe2O3 is what we need in the products. And we need the carbon, okay, Fe3O4 is needed. And we need carbon dioxide. Yeah, so when we keep this as is, so that is bringing carbon monoxide. But if you look at it, these are extra stuff we don't need. So when they are on the opposite side, they will cancel out, right? And when they are on the same side, so what about this one? 1 second, Fe2. So this one also is as is. So here, Fe2O3 is what we need. And we need carbon. Yeah, carbon monoxide comes from that. But some of the carbon monoxide get cancelled out. Carbon dioxide also gets cancelled out opposite. Look at that, carbon dioxide. And there seems to be a mistake here. Okay, this will be gas. This will be gas, okay? And these two guys will cancel out. The only thing, Fe2O3 plus carbon monoxide, we need to multiply this by, multiply as is, but multiply by 3. Okay, this whole thing is going to be multiplied by 3. Why? Because Fe2O3, we need 3 Fe2O3, and that's why there's only 1 Fe2O3. That is why you need to multiply by 3. Okay, we need 3 carbon monoxides. So that's where we are getting this 3 carbon monoxides. That's going to be multiplied by that. No. We need only 1. Okay, let me do this one for you guys. Hold on. Okay, I'm going to do this one for you guys. So Fe2O3, Fe2O3. So this is this good. Next is this one is good. So we are keeping it as is, but multiplying by 3. So 3 multiplied by this whole equation as is. So remember, this guy will also be multiplied by 3. Next is we need Fe3O4 on the product side. So this one also will be as is. Okay. And but we need 2 Fe2O, two of them. So we will have to multiply this by 2. Okay, so this also gets multiplied by 2. All right, now let's do this. Rewrite. So 3 Fe2O3. Okay, plus 3 times 3 is 3 3s are 9 carbon monoxide. Okay, gives you 3 2s are 6 Fe plus 3 3s are 9 CO2. And then 28 times 3, what is that? 28 times 3, somebody do it. And that's a negative number, so that will stay. Okay, next is 2. Say that again. 84, and that's kilojoules, and that's negative. Okay. Is equal to negative 84. Okay, kilojoules. Okay, next is 2 3s are 6 Fe plus 2 4s are 8 CO2 gives you 2 4s are 8 CO plus 2 Fe3O4. And then 2 multiply by this positive 12.5. 12.5 times 2 is what? Say that again. 25? 25 kilojoules. Okay, so this 84 minus 24, 25. Yeah. $59. And the sign of a big number. Okay, so at least this part we're done, but let's finish this. Okay. Now, 6 irons and 6 irons cancel out. 6 iron and 6 iron cancel out. Then 9 CO2 and 8 CO2. That means this leaves us one with 1 CO2 over here. Okay. 9 CO2 and 8. So this leaves us with 1 CO here. Okay. And then you are left with, wait a minute. This is 3Fe2O3 plus 1 CO plus 1 CO2, 1 CO2 plus, and then the last one is that Fe2, 2 Fe3O4 plus. Okay, and it's very important to put the S. Yeah, just make sure that these are the same. This is the same. This should be grams. So this should also be grams. Sorry, not the grams, sorry, gas. Gas. So the gas, solid, gas, and this guy is a solid. So you have the gas, solid, gas, and solid. All right, guys, so that's the way you do it. So just pay attention because I'm going to look at these steps. Given the table for this reaction, once again, write down the formula, the reactants and the products. This one you guys did fine. Okay, the net ionic equations, all this is like this balancing equation, oxidation reduction, look at the oxidation numbers. All right. Now, this is all your stoichiometry stuff. We've covered much of it, but I need to ask you from here, which one you guys were saying? Do which one? 86? Yes. All this is the last part now. We made it. So this is the stoichiometry. Now tell me from the stoichiometry, what do you want? Come on, this is the last part. Okay, let's do this one, the empirical formula. So this guy over here, sulfur, percentage of sulfur converts to what? This becomes what?
27 grams.
Grams, very good. So this becomes, you're prepared. Leila, looks like you're prepared. You're very well prepared. No, it's good, it's good, it's good. I mean, I can understand, like it's very good. Wonderful. Yeah. So 13.4 grams and 59.6 grams. It's very good. I'm happy with that. You know, when the students are prepared, the professors also feel like, okay, maybe, you know, this is a very satisfying feeling. Okay, anyway, so let's do this. So you're given the grams. Grams of sulfur, what will the first thing you're going to do? Moles, yeah. So the grams of sulfur, 27 grams of sulfur. Convert that to moles. One mole of sulfur is how much? Very good, 32 grams. So do this. Then you have 13.4 grams of oxygen times 1 mole of oxygen over the oxygen, 16, just put 16. Some students put 32, 16 grams of oxygen. And the other one is 59.6 grams of chlorine times 1 mole of chlorine over 35 grams of chlorine. Okay, so you're going to get the moles. Let's do this quickly, because I think this one was on the exam also. So 27, divide that by 32, and you get 0.84. Okay, that's the moles of sulfur. Next is 13.4, divide by 16. So this is 0.83 moles of oxygen. Okay, the next is 59.6, divide by 35. Okay, and what do you get here? 1.70 moles of chlorine. Okay, so now what will you do next?
Find the lowest one.
Yeah, so the lowest is similar. I mean 0.84, 0.84, 0.83 is 0.84 only. So you can just make it 0.84. Okay, little bit of, now next is mole to mole ratios. Sulfur over sulfur, oxygen over sulfur, and chlorine over sulfur. So 0.84 over 0.84, then 0.84 over 0.84, then comes the 1.70 over 0.84. So here 1.70 over 0.84. Okay, so divide by 0.84. This one is 2. So this comes out to be 2. This is 1. This is 1. So that means sulfur, oxygen, and chlorine are 1:1:2 ratio. That means SOCl2. This is the empirical formula. Okay, got it? Okay, now this one, guys, the combustion of ammonia in the presence of oxygen yields nitrogen dioxide and water. The combination of 43 grams of ammonia with 258 grams of oxygen produces how many grams of nitrogen dioxide? So here you are going to find the limiting reactant. So certain things are not going to be given to you directly, but that's what it means. So we are testing your understanding, you know. So limiting reactant, because you are given 43.9 grams of ammonia, and you're going to find the grams of nitrogen dioxide. Using 258 grams of oxygen, you will find how many grams of nitrogen dioxide can you produce. And the one which gives you the lowest amount is your theoretical yield, and that is the answer for this one. So you guys know how to do all this? Check I mean, we've done this limiting reactant so many times, so check that. Okay. Here again, a particular experiment, the reaction of aluminum. Same is the case. Grams of aluminum is given, grams of oxygen is given. And you are given, this is the actual yield. Actual yield is given, and they're asking you to find a percentage yield. Okay, so you need to find the theoretical yield, and the theoretical yield comes through the limiting reactant. And so how will you do this? You're going to take 2.5 grams of aluminum, 2.5 grams of aluminum, and you're going to find how much of Al2O3 can you produce. Same is the case, 2.5 grams of oxygen, and how much of Al2O3 can you produce. The one that's giving you lowest, use the lowest amount. So the lowest would be your theoretical yield. Okay, and then you take percentage yield is what? Actual over theoretical times 100%, and you get whatever answer here. All right, guys. So just remember that you start with grams of something, grams of A, convert that to moles of A. 1 mole of A over the molar mass of A, whatever that A is. You're converting A to B. Next is you're going to look at the mole to mole ratio. The number of moles of A, no, the number of moles of B over the number of moles of A. And this piece you're going to get from the balanced equation. Okay, times. Now you can stop here also, but if you're just looking at the limiting reactant. But for these questions, you need to convert. Next is you're going to take 1 mole of B, and this is the molar mass of B. Okay, and that is going to give you the grams of B. So this is the strategy you will follow for this reaction, this problem, and yeah. Okay, and the last is these are the neutralization reactions. What volume of the concentrated solution of magnesium chloride must be diluted with this to make, so here you are using the formula M1 V1 is equal to M2 V2. Okay, got it? That's the dilution formula. Anytime you see the word diluted, you use this formula. Diluted, that's a trick. Okay, and remember that higher the concentration, lower the volume, and lower the molarity, higher the volume. So that's like a relationship. This is a neutralization reaction. In this case, write the balanced equation. Okay. So you are given, so here you are given the molarity and volume is given. So find the moles of sodium hydroxide. So you find the moles of sodium hydroxide, then mole to mole ratio. Find the moles of the acid, in this case it's a perchloric acid, by using the mole to mole ratio. So you take the moles of the base, in this case it's sodium hydroxide, multiply by, this is the number of moles from the balanced equation of the acid over the number of moles from the balanced equation of the base. So that gives you the moles of acid. So that comes from the balanced equation. Okay, once you get the moles of the acid, put that over the volume in liters. You have to convert it into liters to give you that gives you the molarity. But what volume? So in this case, you are given, you need to find the volume. So volume is equal to number of moles of the acid over the molarity of the acid that is given. Okay, so this is what you will do. So guys, I covered a lot already, and all the important things are here for you. Just practice these, and if you don't understand something, you can still ask me. Okay, so I'm going to just stop this, and thank you for your patience.